open the floor to questions, and I'm going to take most of them, and I want you guys to really find the speakers in the break and throughout the course of the next 2 days to ask them your questions. Families in this room should not be scared to approach anybody else in this room. This is your day. The next 2 days is yours. You should go and talk to everybody, you should engage, and you should ask any question you have. But I'm happy to just take some questions that you might be thinking about and try to address them in a way that's pertinent to you and your family. So if we want to ask any questions, otherwise we can go ahead and start the break. I can't, there's a question over there. I can't see anything up here, so if there are runners, it would be really great if you guys can just go and find those people.
Hello, thank you. I have a couple of questions for the John Hopkins set, who explain very well the functions of UBE3A protein. Sorry, the echo is. The first question is if there's any protein accumulation documented wherever the UB3A is lacking or mutated, and also why they do explain the imprinting of UB3A in the brain.
I think I understood your question, and I apologize, there's an echo, so it was a little bit hard for me to understand what you were saying, but I think what you're asking for is there accumulation of UBE3A protein?
No, of other protein, since the UBE3A is not binding its target, is there any protein accumulation documented in the brain whenever the UB3A is not functioning, other proteins?
Right, yes. So because UB3 targets thousands of other proteins, and if it's not targeting and tagging it to be degraded, and in some instances upregulated to not be degraded, so there's a balance of homeostasis. So there's a balance where there's targeting of a protein to say you should be trash, and there's targeting a protein that says you should stick around for a longer period of time. And when you don't have that targeting, meaning the tag, keep and throw, it's completely unbalanced. So there are many proteins that there are too many of them, and there are many proteins where there are not enough of them. So replacing certain proteins could be helpful, or targeting the breakdown of certain proteins can be helpful. And that's why when you think about all of the downstream effects of the function of UBE3A, there's hundreds, if not thousands of them, in the neurons specifically, but probably in other cells of the body as well. But we know in other cells of the body, we have the paternal copy that's being read because it's only silenced in neurons. Yeah. So it's mostly a neuronal disorder. And when you look at the brains of animals, and humans actually, for deceased brains, when you look at the brains after and before therapy, and you can look at what we call proteomics, which is what is the downstream effect, and that signature is very different in Angelman syndrome compared to neurotypical, and it's thousands of proteins that are either upregulated or inappropriately downregulated.
So can we say that maybe that's why we don't see a neurodegeneration in Angelman syndrome patients?
Probably the reason we don't see neurodegeneration is because the imbalance of proteins that's there are not degenerative proteins. So when you think about something like ALS, right, the proteins that are, accumulating are ultimately killing neurons. When you look at Alzheimer's disease, the plaques that are being deposited are killing neurons. A lysosomal storage disease, it's resulting in not degrading certain types of fats that are accumulating in cells that cause cell death. There are no proteins that we know of in Angelman syndrome that cause cell death when they're upregulated or downregulated, which is why anatomically, if you look at the MRI of an adult with Angelman syndrome, it looks relatively normal. There may be some delay in myelin depositing, but the neurons themselves look anatomically normal. And when you see a report on an MRI, it's generally normal compared to what you might see with MPS, Sanfilippo that was just shown, or what you would see potentially with Alzheimer's or ALS or something like that.
Thank you.
Sure. Next question. Okay.
Yeah, just a clarifying question. Oh, the echo is bad.
It's worse for me.
Okay. Regarding Dr. James' presentation, there was a comment that AAV can't be used with UBE3A because of its size. And so just wondering what vectors could be used in current or future trials.
That's a great question. So most proteins, or many proteins, are very large, and or genes are very large, and there's a capacity to a vector like AAV. Generally, it can hold only a certain amount of genetic material. For Angelman, the gene can actually fit in the vector, but the gene itself has multiple isoforms, meaning that when you make UB3A, it's enormous, but there's certain pieces of it that are this big or this big or this big. And the function of those have been tested in these models to show that one isoform, called isoform 1 for the human UBE3A construct, is actually the smaller one, and it has most of the function. So when we give back isoform 1, we see full rescue of phenotype in the animal model. When we give back isoform 2, we don't see great rescue of the phenotype, and actually with too much of it, you can see toxicity. So you don't want to give back too much isoform 2, and isoform 3 practically doesn't exist. So basically what we have shown is that with just isoform 1, you can correct the symptoms of Angelman syndrome. So there are multiple programs using AAV for Angelman syndrome with gene delivery, and they're using isoform 1 because it does fit. And some people are actually mixing isoform 1 and 2 in a shorter form where it together does fit. So that's something that's in discovery at the University of North Carolina. Any other questions?
Is there another question?
Okay, why don't we go for a break? Everyone chit chat, go have some coffee, and we'll be back here at 11.